for bond energies and enthalpies. Atoms are attracted to one another when their outer electrons of one atom are electrostatically attracted to the nuclei of the other atom. Coulomb's force. Opposites attract, negative deposit. The attraction between the two atoms makes them increasingly stable, giving them a lower potential energy. This is why things bond, is to lower the potential energy, which makes them more stable. You want to be up on the edge of a cliff, or do you want to be down in the valley? You want to be down in the valley where you're more stable. However, an atom continues to approach one another and get increasingly close. There comes a point at which the two nuclei, those positive parts, are going to repel each other. As they start to repel one another, the potential energy is going to raise once again, and the two atoms become less stable. So there's this happy area in between, and this is why we have atoms that bond at different lengths. And so where this maximum or this minimum is found is where the potential energy is minimized, and so you have a stable bond, and this is what's that bond length for like a hydrogen atom. Typical plot for this formation of simple molecule of H2 is shown below, so we're going to see that in a second, where 74 picometers and at 436 kilojoules are the bond length and the strength respectively. So here's that diagram. So here you see this is where the minimum potential energy is. This is where the atoms want to be, is this far apart to minimize that potential energy. There's our energy for it. And then we have our length, which is there, and our unit is picometers. 10 to the micro, mellow, and we got negative 12 meters. So really close together. So that's your bond length once again, your bond energy. Since the force of attraction that stabilizes atoms when the bonds are attracted between the electron and nuclei, the greater the number of electrons involved, the stronger the attraction. Such triple covalent bonds tend to be stronger than double bonds, and double bonds tend to be stronger than single bonds. Shorter bonds also tend to be stronger than longer ones, so if you're close together, you're probably going to be stronger. Think of it as like you're holding a football. If it's held close to you, it's harder to take away. The strength of the bond in diatomic covalent molecules is the bond dissociation energy. How much energy does it take to break a bond? And it always takes energy to break a bond. For example, a hydrogen H2, when I break it apart into its two atoms, the bond energy is 436 kilojoules. It takes 436 kilojoules of energy to break that bond. We have polyatomic elements or molecules, for example. Methane has 4 identical CH bonds, but each has a different bond dissociation energy. These are only approximate values, and it's because as I take away the hydrogens, those energy change. It's kind of like the ionization energy we saw. So to take away the first bond takes 440 kilojoules, the second bond 460, 420, and then to take away that last bond is 430 kilojoules. So why do we have endo and exothermic reactions? It depends on what bonds are broken and what bonds are made. If the total energy needed to break the reactants bonds is greater than the total energy released in making the product bond, then the reaction or the system is endothermic. It took in energy. It took more energy to break bonds than what it released. As a result, the temperature of the surroundings drops. In an exothermic reaction, the total energy needed to break the bond and the reactants is less than the total energy released by making the product bonds in this system is exothermic. So hey, we've got energy out because of those new bonds being formed. As a result, the temperature of the surroundings rises. Some average bond energies are given on this table below, which is really the next page. So we got this table, and these work in general. This is not always like perfect. It depends on the arrangement of the atoms and stuff. F bond's always going to be 156 because that's the only way you can have it. But the CO bond will depend on what's bonded to that carbon. So this is only an approximation.